In today's video, we will talk about the calculation for elastic section properties for steel plate I-girder bridge. The example bridge shows in the plan view has 4 girders, G1, G2, G3, and G4. Only the center line of each girder is shown in the plan view. As of section AA on the bottom, the overhang of the bridge is 3'6", and the girder spacing between two adjacent girders is 10 feet. The girders are supporting concrete deck on top, which is 9-inch thick. Some material properties for concrete, the weight of the concrete is 0.15 kg per cubic feet. The concrete strength, FC prime, is 4 KSI. The elastic modulus of steel is 29,000 KSI. We will calculate 3 different section properties. The first one is non-composite section, which only have the steel girder. The second one is long-term composite section using 3N, and we will talk about N later. The third one is short-term composite section using N. And when we talk about composite section, it means the section will consider both concrete deck and the girder. N is defined as modular ratio per AASHTO era FD 9th edition, equation 6.10.1.1.1b-1. N is defined as E divided by EC, which in this example, E is the elastic modulus of the steel girder, which is 29,000 KSI. And EC is the elastic modulus of concrete, which is defined as this equation. This equation is in AASHTO era FD 9th edition. It's equation C 5.4.2.4-2. And plug in all the numbers, which WC is the concrete weight, which is 0.15 kcf. FC prime is concrete strength, which is 4.0 KSI. And K1 here, usually we're taking as 1.0 unless approved otherwise. So after plugging in all the numbers, EC is calculated as 3,834 KSI. And when we plug in E and EC to this N equation, we will get N equal to 7.56. First, let's calculate the non-composite section property, which again only have the steel girder. So here on top, we have the dimension of this steel plate I-girder, which top flange is 1 inch times 18-inch plate. The width is 9/16 of inch times 84 inch. And the bottom flange is 1 3/4 of inch times 21 inch. All right, let's complete this table down here. So top flange, the area is 1 inch times 18 inch, which gives 18 square inch. And D is the center line of the top flange. To the center line of to the axis which we're calculating the moment of inertia for. So first let's define our neutral axis as center line of the web. So D, it's calculated as 1 inch divided by 2 plus 84 inch divided by 2. Again, 1 inch is the thickness of top flange. And 84 is the depth of the web. So this will give 42.5 inch. And AD is simply using 18 times 42.5, which is 765 inch to the cube. And 80 square is 18 times 42.5 square, which is 32512.5. And I naught here is the moment of inertia of the top flange about its own neutral axis, which is BH cube divided by 12 equal to 18 inch times 1 inch to the cube divided by 12 equal to 1.5 inch to the fourth power. In I, which is the moment of inertia about the neutral axis of the section, actually it's not neutral axis, it's the axis that we're calculating the moment of inertia about, which in this example we set this as the center line of the web. So I equal to AD squared plus I naught, which gives 32512.5 plus 1.5 equal to 32514. Now come to the web. The area of the web is 9/16 of inch times 84 inch, which gives 47.25 inch square. And again, because this section we're calculating about the center line of the web, so D is really 0 here. Therefore, AD is 0. AD squared is 0. I naught is the moment of inertia of the web about its own center line, which is 9 divided by 16 times 84 to the cubic divided by 12, which gives 27783. And I here also equal to 27783. Now bottom flange, the area is 1/3/8 of inch times 21 inches, which gives 28.875 inch square. And D here, because bottom flange is below the CR web, which we can define if anything below the center line of web, we just give a negative number. Anything above, we give positive number. So earlier when top flange, all the numbers are positive, as we already calculated. So now I come to D for the bottom flange. It's equal to negative 84 inch divided by 2, which is half of the web depth, plus 1.375 inch divided by 2, which is the thickness of the bottom flange, and we'll get negative 42.6 2.69. Now again, AD squared is 28.875 times the negative 42.69 squared, which gives, this is 80, so it's negative, there's no square here, and which gives negative 1232.6. And 80 squared is 28.875 times negative 42.69 to the square, which gives 52616.7. I-girder is 21 inch times 1.375 to the cube divided by 12, which gives 4.55 inch to the fourth power, and I equal to 52616.7 plus 4.55 equal to 52621. Now come to the whole section. We already calculate individual components and the top flange, the web, and the bottom. So now we are going to look at the complete section here. So just simply sum up all these areas. So we will get the total area of the girder equal to 18 plus 47.25 plus 28.875 equal to 94.125. The summation of AD, it's 765 minus 1232.6 equal to minus 467.6. And total I is 27783 plus 52621 gives 112918. Now for the whole section, the CG of the section is calculated as the moment of inertia, which is 112918, divided by total excuse me. D is the summation of AD, which is minus 467.6 divided by the total area, 94.125. So give the CG of the whole section is negative 4.97 inches. And for the whole section, the ASDS squared equal to 94.125 times negative 4.97 to the square and again, because this is below the neutral axis, because dx we calculate as negative, so this whole thing will be negative, and which gives negative 23.972. And the moment the inertia all above the neutral axis, it's 112.918 minus 2323.972 equal to 110.594 inch to the fourth power. Now, the distance between top of the steel to the neutral axis. So come back to the this section on top. This is the neutral axis that we calculated, and this is the top of the steel. Therefore, we can calculate as 1 inch, which is the top steel flange thickness, plus 84 divided by 2, plus negative 4.97. Plus the 4.97 inch, because from top of the steel to this NA, we should add this additional 4.97, and this gives 47.97 inch. And to the distance between neutral axis to the bottom of steel, this is the bottom of steel. So we're talking about this distance, which is calculated as 1.375. This is the bottom steel flange thickness, plus 84 divided by 2, and minus 4.97. And this gives 38.41 inch. Now the section modulus of the steel girder is calculated as 110.594, which is the moment of inertia about the neutral axis we calculated earlier. Divide by the top of steel, 47.97, equal to 2,305 inch to the cubic. And section modulus with respect to the bottom of steel, it's 110.594 divided by 38.41. Which gives 2,879 inch to the cubic. So this complete the elastic section modulus section properties calculation for non-composite section, which have the steel girder only. Now let's move on to the long-term composite section using 3N. Now here on top, the section shows the steel girder and the concrete deck altogether. And the effective flange of effective width of the concrete deck is calculated as 3 foot 6 inch, which is the overhang, plus 10 foot girder spacing divided by 2. There's no inch here, which gives 8 foot 6 inches. This is simply calculated based on the tributary area of the concrete deck. Now come back to the table, similar as before, but now the component becomes the steel section, which we already calculated previously, and the concrete slab. Remember, this is long term using 3N. So this 3N will be reflected here in the concrete, which is the concrete area divided by 3N equals to 22.68. So now the steel section as we calculated earlier, A equal to 94.125. So we just simply move it here, 94.125. And then AD here, it's negative 467.6. So we just move it here for negative 467.6. In the I, it's 112.918. Again, copy here, 112.918. Now come to the concrete slab. The area is 9 inch times 102 inch, which 102 inch is the effective width of the concrete slab. And this whole area divided by 22.68, which is 3N. And this gives 40.48. D here is 84 divided by 2, half of the girder depth, plus 4 inch. The 4 inch here is the haunch, then plus 9 inch divided by 2. 9 inch is the deck thickness, and this gives 50.5 inch. AD is 40.48 times 50.5 equal to 2044. AD squared 40.48 times 50.5 squared equal to 103.234. I naught, it's 102 times 9 to the cube divided by 12. And this whole thing needs to divide by the 3N, which is 22.68, equal to 273.2. And I equal to 103.324 plus 273.2, which gives 103.531. Now the total area, 94.125 plus 40.48 equal to 134.61. the sigma AD negative 467.6 plus 2044 gives 1576. The I, it's 112918 plus 103531, which gives 216449. A3n times D3n squared. So first calculate D3n, which equals to 1576 divided by 134.61. Again, this is the summation of the AD divided by the total area of the composite section. This is just simplifying the CG of the section, which gives 11.71 inch. Now A3n D 3n to the cube, we can simply calculate as negative 11.71 times 1576 gives negative 18,455. And INA equal to 216,449 minus 18,455 equal to 194,994 inch to the fourth power. So distance between top of steel and the neutral axis of the composite section is calculated as the top of steel is calculated as 1 inch plus 84 divided by 2 plus 11.71. Which gives 31.29. Now here we need to minus that because now the D3n is positive. So which means the D3n, the neutral axis of the composite section, it's on top of the it's on top of the center line of the girder we assumed earlier. We used to calculate the section properties earlier. Now the bottom of steel is 42 plus 1.375 plus 11.71 equal to 55.085 inch. Now the section modulus to the top of the steel, it's 197,994 divided by 31.29, which gives 6,000 328 inch to the cube. And section modulus to the bottom of the steel, it's 197,994 divided by 55.085 equal to 3,594 inch to the cube. Now this complete the elastic section modulus for the long-term composite section using 3N. Now let's move on to the last part. The short-term composite section modulus using N equal to 7.56. The same section cross-sectional sketch here as the long-term one. The only difference between the long-term and short-term composite section calculation is only the 3N versus N for the short-term. So now we can quickly calculate, finish this table. Again, as we calculated earlier, A is, for the steel section, is 94.125. The AD is negative 467.6. And the I is 112,918. The concrete slab calculated based on N, its area is 1 to 1.43, which is 9 inch times 102 inch divided by 7.56. The D is same as the long term, which is 50.5. AD is 1 to 1.43 times 50.5 gives 6,132. AD square is 1 to 1.43 times 50.5 to the square equal to 309,677. I naught is 102 times 9 to the cube divided by 12 divided by 7.56 equal to 819.6, and I equal to 309,667 plus 819.6 equal to 310,497. The summation of the total area is 215.555. Summation of AD is 5,664. The summation of I is 423,415. And AN DN square is negative 26 point, here DN come here is 5,664. So here the summation of AD divided by 215.555, which is the total area, equal to 26.28 inch. And here the ANDN square is negative 26.28 times 5,664 gives negative 148,850. And sigma moment of inertia about neutral axis is 274. 565 inch to the 4th power. The distance between top of steel to the neutral axis is calculated as 1 inch plus 84 divided by 2 minus 26.28, which gives 16.72 inch. The bottom of steel, it's 1.375 plus 84 divided by 2 plus 26.28, which equal to 69.655 inch. The section modulus to the top of the steel is calculated as 274,565. It's the moment of inertia of the composite section divided by 16.72 inch. It's equal to 16,421 inch to the cube. And the section modulus to the bottom of the steel is calculated as 274,565 divided by 69,655 equal to 3,942 inch to the cube. This complete the elastic section modulus for non-composite section, which I have steel only, the long-term composite section using 3N, and the short-term composite section using N.